Hello class, sorry I can't be with you here today, but we are going to review related rates. So feel free to pause the video anytime you need to. If you want to go back to retrace your steps, go ahead and rewind it and whatnot. So once again, we will be starting with related rates. So as you guys know from last year, related rates is pretty much problem solving. So we know how to do the calculus, but now we need to figure out what does it mean in the real world. So every problem that you have will require some kind of real world answer at the end. So it's not enough to just solve the problems, but tell me what it means in real life. So here are your steps. First thing is to understand your problem, and just like before, always do your find when given. The problem will clearly ask you what you're looking for. Since we're using time when we are looking for this, given different things. So they could give us a rate, they could give us a side of the wall or whatever it may be, but you'll always have these three pieces. Next part is to draw a picture. So making sure we can draw the picture helps us know that we understand what the question is saying, but also label the parts. So just like in chemistry where you had to have your units, your answers will also have to have its units here. Step 3 is to write your equation. Typically it's some kind of trigonometry equation, or it might even be a geometry equation. You can find these equations inside your textbook. For today, I will be providing them for you. So write your equation. Second part is where you start the calculus. So differentiate, which means take our derivative, right? And since we are doing rates of change, you need to take all the derivatives of every single variable that we're using. Finally, substitute all the numbers you know, and then do the algebra. And then tell me what this means in the real world, okay? So hopefully you got all of that down, and we will be doing the first problem right now. Okay, so a hot air balloon problem. You are going to be doing some of these on your own, so make sure you pay attention to all the steps. But as it says a hot air balloon is rising straight up from a level field and is tracked by a rangefinder 500 feet from liftoff. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. So how fast is the balloon rising at that moment? Okay, so what is my find? What am I looking for? Well, if I look, the question is saying, well, how fast is the balloon rising? So that's the real world question. But when I'm doing this, what exactly is that variable? So what I'm going to do is I'm going to actually skip ahead to the picture so we can see what this is supposed to look like. So here's my hot air balloon, right? And we're seeing how it rises. So since our hot air balloons rise going up, isn't how fast it's rising depend on its height, right? So I'm going to start here at ground level. So just to sketch it out for you guys. Start at ground level, and I know that the balloon has to go straight up. Okay? And this is a variable since I know it's not going to stay in one place. I'm just going to call it h because that's the height of something. I also know that there is a rangefinder somewhere over here, so I'm just going to mark it right here. That's actually scoping out to see where is this going to be. So what shape does this look like? Yes, a triangle. So we are going to have to do some kind of trigonometry for this problem. Let me just group my picture over here. going to make this smaller so I can make room for all our other information. Okay. So what I'm actually trying to find is how fast it's rising. I don't want to know where it is. I want to know how fast it's rising. So since it's how fast something is, isn't that our rate? So I want to find dH dt. When, right? So if I look for when it's rising, it says, well, at the moment the elevation is pi over 4, and the angle is increasing at this rate. So my when is the actual angle pi over 4. Okay. So I'm looking when theta is equal to pi over 4. And my given is the other rate that we have, which is when I know this part right here. Given my rate of the angle is pi, 0.14 radians per minute. Okay, so if this is a rate, how should I write it under my given section? So if I go into this, I should actually write this as d theta dt is equal to 0.14 radians per minute because of this word right here. It's a rate, so I know it's a derivative of the angle. Okay, good. Any questions? Just kidding. I can't really answer them right now, but you have each other to help each other out. Okay, so now I have to figure out what equation I need to use. So I have a theta, I have a triangle. I know it has to be one of the trig equations, but now I have to take a look at what this is saying. So I didn't finish labeling my picture. There's another number in here that is important in our problem, which is this word 500 feet. The rangefinder is 500 feet from liftoff. So does that piece of this change? No, right? I can't move that tracker. It's going to stay there, but I am going to label this as 500 feet. If my balloon is rising vertically straight up, what angle is formed right here from the liftoff point? It's in a 90-degree angle, right? So if I'm looking at thetas, I'm looking at angles. I know I can do work with hypotenuses, but for this problem, our most important part is, well, what is this rate? So the equation we should use is from SOHCAHTOA. So the only pieces of information I have right now are this height and this right here. I have no idea what this hypotenuse is, so I can't use this, which means I'm going to use my angles to figure out what equation this should be. What does this angle theta stand for? This angle right here actually stands for the theta of how the angle of the finder is increasing as the balloon goes up. So now that I have this, I can use our information of SOHCAHTOA. So I'm going to write that right here. SOHCAHTOA, right, to answer this. So if I take this theta right here, what equation uses the opposite and the adjacent one? So if I look here, I see that it's tangent. So for my equation, I know the tangent of theta is equal to the opposite, which for here is right here, our h, over our adjacent, which is the adjacent section, which is 500. And now I have an equation that I can use. go ahead and copy this down. I'm going to start a new page so that we can actually start step 4. So right here, I know tangent of theta is equal to h over 500. So if I were to take this derivative, what's the derivative of tangent? Okay, so secant squared theta. Since I took the derivative with respect to theta, I need to put in d theta dt. What's the derivative of h over 500? Well, it should be 1 over 500 and then dh dt. Right? So if I go back to my previous page, what are we actually trying to find? I'm trying to find dh dt. So I'm going to move everything around so I get dh dt by itself. So to get this by itself, I need to multiply everything by 500. Multiply there, multiply this by 500, and now I get this equation, dh dt equals 500 secant squared theta d theta dt. Good. And just like step 5 says, plug in all your information. So if I plug this in, I get d theta dt equals 500 secant squared of pi over 4, and our d theta dt was equal to 0.14, so 0.14. Good, and this was right over here. Plug all of this into your calculator, or we can do it by hand, right? So if I do this by hand, d theta dt equals 500. What's the secant of pi over 4? Yes, know your trig chart. So square root of 2 squared, right, because of this right here. Then 0.14. And then you can do it by your calculator or whatnot. So 500 times, these cancel, so 2 times 0.14. That gives me 1,000 times 0.14, which means I move my decimal 3 times. So my answer is 140. If this is, oh, sorry, this should be a DH right here. DH. If this is DH dt, I know it's a rate. So my height is actually measured in feet, and my time is measured in minutes. So this is how fast the hot air balloon is going up in the air. Okay, so I'm going to stop this video here and give you some time to work on these problems. So if you take a look at the worksheet you were given, I'd like you to try exercise number 11. So exit slip, worksheet number 11. Alright, so here is part 2 of our lecture. Hopefully you're able to get the answer to number 11. But we will be doing another triangle problem that actually does not look at theta anymore. So a police cruiser is approaching a right-angled intersection from the north, is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with the radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles at the instant of measurement, what is the speed of the car? So if I'm trying to find this find when given, right, I'm actually trying to find a rate. Isn't speed a rate? Speed is the distance over time, which is a rate, right? It's a change over time. So what I'm trying to find here, I'm going to call the car who's getting chased, who's probably going to get the ticket, I am going to call them, actually, let me fix this. I'm going to call them X. Since I want the speed of X, right here, this should be dx dt, right? So just to highlight that, I know it says what is the speed of the car. Okay. Second thing is when. So it says if the cruiser is moving at 60 miles per hour, so I know I want it to be when this is 60 miles per hour. Okay. And the cruiser is the police, so I'm going to call this Y. If this is a speed, what does that tell us? Anyone? Well, if it's speed, it's telling us they're moving when dy dt is equal to 60 miles per hour. Questions? No? Well, there's another rate that's given in here, right? It says, at the second part right here, it says distance between the car is increasing at 20 miles per hour. So since I'm using x, y, and z, since I'm using x, y, I'm going to call this one z. And dz dt is actually equal to 20 miles per hour. Now, what other information do they give us? Let me move these down. Well, what it's saying is, well, when the cruiser is 0.6 miles north and the car is 0.8 miles east, that's when I'm trying to take a look at these areas. So if the cruiser right here is right here, and the cruiser is which variable, x or y? It's y. So, oops, sorry, let me erase that right there. Okay, so my cruiser is going to be 0.6 miles north, right? And I want my car, which is x, to be at 0.8 miles east. So all this information is needed to solve this problem. Okay. Let's draw the picture just so we can make sure we're all on the same page. Here is my intersection, right? It's telling me that the cruiser is 0.6 miles north. So this right here is where my popo is, right? My police car is right here. So I'm going to label this as my y, right? Just like a normal XY grid. The car who's being chased is 0.8 miles east, which is right here in this direction. Right, so I'm going to just call this C for car. And we're going to call this X. So at any given period, this is not exactly, I don't really know exactly where these cars are. All I know is this car is moving from here to here, at the same time the police car is trying to chase it to go that way. Okay, so we're trying to find its speed at these two particular times. So the distance between the police car and the guy who's getting chased is whatever this distance is. And with that, what shape do I create? A triangle. So once again, we're going to do more triangle work. And if this is an intersection, what kind of angle is this? It's a right angle. And now I can do work, right? So if I'm using a 90-degree angle, and this is a triangle, or a right triangle, what is the famous equation that we usually tend to use? Good, Pythagorean theorem. So I'm actually going to move this equation to the next page, but hopefully you have this picture with you. So if I look at the equation, I have x squared plus y squared is equal to z squared. Right? Good. So I have my equation. Next step is to take the derivative. The derivative of x squared is 2x. Since I'm doing rates, I need to say dx dt, right? Derivative of y squared is 2y. And then I also have to say dy dt. And what's the derivative of z squared? Same thing. 2z dz dt. Good. Now I can plug everything in, but if you notice, I can factor out these 2's. So this cancels, that cancels, and this cancels, and I just get x dx dt plus dy dt times y equals z dz dt. Well, now I actually need to find all these values. I know my x, right? It gave me that my x was going to be 0.8 miles. I know my y is 0.6 miles. I'm looking for my dx dt, but I'm given my dy dt. I'm given my dz dt, but am I given my z? No, I'm not. Indirectly, I am. So if my x is 0.8 squared, and my y is 0.6 squared, and this is equal to z squared, can I use algebra to find my z? Yes. So I get, if I solve all of this, I get, square root of 0.8 squared plus 0.6 squared, and my z is equal to plus or minus, what do we get? Z is equal to, what do you guys get? You should get 1, right? 0.64 plus 0.36 is equal to 1. Square root of 1 is 1. So I get this. But since this is a real world problem, which one should I use? I should use my positive one. So my z is equal to 1. Okay. So I'm going to shrink this off to the side. Just give me a minute. I'm going to put this here in case you guys need it. You can just rewind. Then now I'm going to plug all this information in. Okay. My x was equal to 0.8. I'm looking for dx dt. My y is equal to 0.6. What was my dy dt equal to? I listed dy dt as 60 miles per hour. If I'm taking a look at this picture though, if my dy dt is telling me how much further away this police car is going down, shouldn't I actually make this a negative dy dt? Because I'm looking at the direction. I know that this police car is going 60 this way. If it was positive 60, I'd be going this way. But I want to make sure I'm telling my problem where we're actually going towards the intersection. So for here, I'm going to plug in negative 60. I have my z is equal to 1, and my dz dt was equal to 20. If we do this algebra, you should get dx dt is equal to 70. Since it's a speed, it should be 70 miles per hour. So this cop is, I'm sorry, not the cop, but the guy who is going to get caught and running away from the cops is actually driving at 70 miles per hour, which in the real world at an intersection is illegal, and he will probably get this ticket. Good. So now what I would like you guys to do is I'd like you to try exercise number 13. So second part of your exit slip is this worksheet number 13. Good luck. Okay, so here's our last example. It's a little more difficult, but we are still kind of using the idea of triangles, except now it's a 3D figure, and we will be looking at volume. The water runs into a conical tank at the rate of 9 feet cubed per minute. The tank standpoints down and has a height of 10 feet and a base of radius 5 feet. How fast is the water level rising when the water is 6 feet deep? So, if we take a look at this, right, my find is how fast is the water level rising. Since it rises, that means we're looking at a height. So my find is dh dt, right? So that is right here. How fast? My when is when the water is 6 feet deep. So depth is telling me how high I'm actually looking it to be. So I know I want this when my h is equal to 6 feet. Given, what's my given? My given is this rate right here. So if you notice, our givens are always these rates. Since it's a rate, and it's 9 feet cubed per minute, what measures in cubes? This should give you a hint. Good. It's our dV dt. Our volume is changing at this rate. Now you might be asking, well, what the heck is this information here? This base and the feet? Well, that's just what size our tank is. So let's draw this picture. It says the point is down. A conical tank is a cone, right? So I need to have these pieces right here. What this right here is saying, what this right here is saying is this actual cone has a radius of 5 and a height of 10. I can't change the size of the actual cone. I'm just changing the size or the amount of water that trickles in here. And I'm starting to measure all of those pieces out. Okay? So if you need an idea, this is what we're trying to look for in our problem. So I know I have to deal with volume because I've been given a dV dt. So if we look back into our problem, the volume of a cone is actually equal to this right here. Oops, let me make this bigger. The volume is actually equal to V is equal to 1/3 pi r squared h. So this is doable, but there is one problem. Can anyone see what the problem is? I have too many variables. I have a V, I have an R, I have an H. Just like in optimization, if I can get rid of one of my variables, then this will actually help so much more. So what we're going to do is we are going to redraw this picture on the next page and see how we can get rid of it. So if I redraw this, going down, I told you this is 5 feet, and this is equal to 10 feet. Okay. So if I wanted to create a ratio, isn't 5 equal to my R and 10 I can say is my H? Well, the ratio of R over H is equal to 5 over 10. Correct? Since this is what I have, what I can actually say is R is over H equals 1/2. And now I can actually solve for one of these variables. I don't know, let's just solve for H. So if I were to do this, this way, I know H is actually equal to 2R. Okay, I could also say that R is equal to 1 over 2H, right? Isn't this equal to 1/2? So if I wanted to, I can move that over. Now the hard part is, do I use the H or do I use the R? So I'm going to go back to our problem. And what information do you have over here? Well, I'm looking for dH dt, so shouldn't I try to solve everything for h's? So what I'm going to do is, I'm going to change everything to have this h, and I'm going to use this right here. Okay. So I do a new page. We said volume is equal to 1/3 pi r squared h. But we just said h is actually equal to, we actually said r is equal to h over 2, right? So if I'm going to plug this, into here. What I get is the volume equals 1/3 pi times h over 2 squared h. If I simplify, I get 1 over 3 pi h cubed over 2 squared is 4, so this becomes a 4. And if I simplify even more, I get 1 over 12 pi h cubed. Okay. Now can I take the derivative of this? Yes, so if I take this derivative, I get dv dt is equal to 1 over 4 pi h squared dh dt. Now I can use algebra to solve for dv dt, or I can plug in and then find the answer. I'm actually going to do some algebra to get this by itself. So I know dv dt, I have to multiply by 4, but divide by pi h squared. So I do 4 over pi h squared is equal to my dh dt. I plug that information in. So if I go back, dv dt was equal to 9. dv dt is equal to 9 times 4 over pi. I wanted my h to be 6 squared. I get 36 over 36 pi equals dH dt. These cancel and they get 1 over pi equals dH dt. Which means my height is changing 1 over pi feet per minute, which is approximately 0.32 feet per minute. So what I want you guys to do is I would like you guys to do on your worksheet as your last exit slip, number 17, I believe, yes, number 17. So feel free to stop and play all these videos if you need to. I will also be posting them up on Edmodo when I get the chance, probably on Thursday evening after you've seen the lecture. You will need to complete some of these problems for homework. They will all relate to related rates. So for homework, please do the following problems on your worksheet. Worksheet, page 256 to 258. Number 10, number 12. I believe I had you do number 11, 13. Let's do 14, 18, 19, 22, 23, 24. And I'd also like you to do some of the test questions, the multiple choice. Good luck, ladies.